Greetings of this session. In this session, we will concentrate on concepts of node voltage analysis. This node voltage analysis is a method to find system parameters such as current through the branch or voltage across the branch or the power using a node voltage technologies. So procedure for solving network using node voltage analysis. So first step, identify all the nodes. What do you mean by nodes? Nodes is a point where three or more elements are connected. Nodes is a point where three or more elements are connected. Such point is considered as a node. So first step, we need to identify such all possible nodes, and among those, any one of the node as a reference node. Any one node, but you can give a preference that maximum element connected node you can consider as a reference node. Second step, convert all practical voltage sources to practical current sources. Similar to the mesh current analysis, here you need to convert all practical voltage sources to practical current sources. Next, assume node voltages to each node except reference node. So all the nodes what we identified in the first step except the reference node, to all the nodes you need to assume some node voltages V1, V2, V3, something like that. Then write node voltage equation by applying KCL at each node except reference node. So except reference node, you need to apply KCL, Kirchhoff current law, to all the node. So you will get a set of equation that is equal to n, where n is a number of nodes. So number of equations and number of unknowns remains same. So in the next step, using Cramer's rule, solve node voltage equation and find node voltages. So using Cramer's rule, you need to find node voltages, and using node voltages, calculate required parameters. Once you get the voltages across the element, and using the resistance or impedance, you can find out the current or the power, anything. So we will consider one network, general network. So let us consider this is a general network. So in this, first identify the nodes. Which are the nodes available in this network? So one is this point where 1, 2, 3, 4 elements is connected. Here is the another point 1, 2, 3. Here is the another point. So 3 nodes are available. So out of 3 nodes, you need to consider any one as a reference node. So I will consider this as a reference. So I connected to ground, and these 2 nodes I am assuming the node voltages. Since in this network no practical voltage source or exist, so you need not convert a practical voltage sources to current sources. So first step, second step, and third step, assuming a node voltages to the nodes except the reference node. What is the next step? Next step is to apply KCL to all the nodes. Correct? Applying KCL to all the nodes. So I will consider the node V1 and I will apply KCL to this node. So what is the KCL says? Sum of the current at node is equal to 0. Sum of the current at node is equal to 0, or sum of the incoming current is equal to sum of the outgoing current. So for the source currents, the direction is indicated. So based on the direction, you can consider it as an incoming current or outgoing current. But in the passive elements like R1 and R2, how to assume the direction? So here I am writing the node voltage equation or applying KCL to node V1. So I will consider V1 is of the higher potential with respect to the other node voltages. So when V1 is a higher potential with respect to the other node voltages, current direction is outgoing current. So in the passive element R2, outgoing current is current direction is from V1 to V2, and in R1 is V1 to reference. So what is the current in R1? V1 minus 0 divided by R1, and it is outgoing current. So direction, what is the direction? Some of the incoming and some of the outgoing. So I am assuming all the incoming currents are as a positive and outgoing currents are as a negative. The reason is whatever we will gain, it is a profit. Whatever we are losing, it is a loss. So profit is defined by a positive sign and loss is indicated by a negative sign. So based on the same concept, I am considering all the current entering this node as a positive and all the current leaving from the node as a negative. So by applying KCL to node V1, what is the equation I will get? I1 is the incoming current minus I2 because outgoing current. These are the source current. So I1 minus I2, correct, minus V1 by R1 because this is the higher potential. V1 minus 0 by R1 is the current flowing and it is flowing from V1 to 0. So outgoing current. So minus V1 by R. Here current direction is outgoing. So V1 minus V2 by R2 minus equal to 0. Now I'll take source currents to the other side and drawing current to the other side. So V1 by R1 plus V1 minus V2 by R2 equal to I1 minus I2. Then I'll rearrange in terms of the coefficient of V1 and V2. So V1 into 1 by R1 plus 1 by R2 minus V2 into 1 by R2 equal to I1 minus I2. As we know, 1 by resistance is equal to conductance. So 1 by R1 I will take it as G1 plus G2 into V1 minus V2 into G2 is equal to I1 minus I2. This is the equation 1. Now similarly apply KCL to node V2. So when we are applying KCL to node V2, only one source current based on the direction you have to assign a sign, and this is the equation we are writing for node 2. I will consider V2 is a higher potential compared to other one. So here also I am considering the current direction as outgoing only from V2, and the expression is V2 minus V1 by R2, and this current is V2 by R3. So by applying KCL to node V2, I2 minus V2 minus V1 by R2 minus V2 by R3 equal to 0. Once again simplifying this, so V2 minus V1 by R2 plus V2 by R3 equal to I2, separating in terms of the coefficient of V1 and V2, minus V1 into 1 by R2 plus V2 into 1 by R2 plus 1 by R3 equal to I2, same as minus G2 V1 plus V2 into G2 plus G3 is equal to I2. Now in these two equations, G1, G2, I1, I2, G3 all are the known things. Only unknown is V1 and V2. That is the node voltages what you have assumed. So two equation, two unknowns, solve using a Cramer's rule. So you will get V1 and V2. Once you get to V1 and V2, we can find out the all other required parameters. Current through I2 if it is required, V1 minus V2 by R2. Current through R3 if it is required, V2 by R3. Current through R1, V1 by R1. Correct? So like this, for the given network, we need to write node voltage equation, that is equation 1 and equation 2. This is the case for with two nodes, network with two nodes. Now what is the general node voltage equation? Now G11 V1 plus G12 V2 plus G13 V3 G1n V1 equal to sigma I1. G21 V1 plus G22 V2 plus similarly equal to sigma I2. In this, what are the values? Gij, that is G12, G13, G32, Gn1, all those things. Gij equal to minus conductance in the branch common to node I and J. So G12 is a conductance, negative of conductance connected between the node, element connected between the node 1 and 2. Gii, it is the sum of conductance connected to node I. G11, it is the sum of the conductances connected to node 1. Right? Now II, this II, it is the value of the source current connected to node I. So this is the node current connected to node 1, and it is positive if incoming to the node and negative if outgoing from the node. Now remember one thing, this is the standard form based on the assumption what I made in the previous slide. That is, in the beginning while applying a KCL, current entering the node is considered as a positive and current leaving from the node as a negative. And for every node, while writing a current expression in the passive element, I am considering the node for which I am writing a node voltage equation as a higher potential compared to other node voltages. So these two assumptions you need to do. Now next is the concept of supernode. Concept of supernode in the sense, now consider this network. In this, between node V2 and V3 there is a source voltage, ideal voltage source. So whenever there is an ideal voltage source connected between the node, in that case what will happen? We can't write the expression of the current through this voltage source because no passive element is present in the network. So in such a cases, what to do? So there exists the concept of supernode. That means whenever an ideal voltage source is connected between two nodes, then these two nodes form a generalized node called as supernode. That means in this case, these two nodes together form a generalized node. Now this node is called as a supernode. So how to proceed? So here in this network there are total 3 nodes, V1, V2 and V3. So to write the node equation, to find V1, V2 and V3, we need 3 equations. So one equation I can obtain from, one more thing. Here is one more node is there, V1 as well as a reference. Ideal voltage source is connected. So in such a case, how to obtain the equations? How to apply KCL to each node? Correct? Now in such a case, whenever supernode exists, and supernode is such a way that one of the ideal voltage source is connected between one of the node and a reference node, or it may be between two nodes. Now let us consider this case. Whenever an ideal voltage source is connected between one of the node and a reference node, then I can write the equation directly based on the sign convention of the source voltage. Now higher potential of this voltage source, capital V1, is connected to small v1, node voltage. Lower potential is connected to ground. So this V1 positive side minus 0 equal to the source voltage. So V1 minus 0 equal to capital V1, source voltage. Now similarly, if I come to this, V2 positive side, higher potential is connected to small v2 and lower potential is connected to V3. So V2 minus V3 equal to capital V2. V2 minus V3 equal to capital V2. So two equation I got. So how to obtain the third equation? Now third equation is obtained by applying KCL to this supernode. That means I am applying to KCL to the node, the supernode. That means I need to consider the elements which are connected to V2 as well as which are connected to V3. Now while applying KCL to supernode, now what is the current flowing through this? V2 minus V1 by R1. And since V2 is one of the node in a supernode, I am assuming this is the higher potential, so outgoing current. So minus V2 minus V1 by R1 minus V2 by R2, because this is the higher potential I am assuming. So outgoing current V2 minus 0 by R2 minus V2 by R2. V3 minus V1 by R4, outgoing current once again minus V3 by R3 minus V3 by R3 equal to 0, because none of the source current is connected to this supernode. So it is 0. So by rearranging, so all multiplying with the positive sign, negative sign, so it becomes positive. V2 minus V1 by R1 plus V2 by R2 plus V3 minus V1 by R4 plus V3 by R3 equal to 0. By simplifying, I will get minus V1, separating with respect to the coefficient V1, V2 and V3, minus V1 into 1 by R1 plus 1 by R4 plus V2 1 by R1 plus 1 by R2 plus V3 1 by R3 plus 1 by R4 equal to 0. Now this equation 1, 2 and 3 represents the node voltage equation. Now these three node voltage equation and three unknowns V1, V2 and V3. So three equation, three unknowns. So there is an exact solution. So we can find the value V1, V2, V3 using Cramer's rule. So in this session we have studied how to find network parameter using node voltage analysis. Okay, I hope all of you understood how to find network parameters. Thank you.